I'm doing really great. Thanks for having us. We're looking forward to it. Yep, looking forward to it. Oh, is that me? I'm not muted. They say they can't hear you, so everybody, welcome to the Conspiracy Cat Show. They, they can't hear you. Welcome to my new channel that I've just taken over. Oh dear. No, but I think they can. I think they say
Yeah,
they can hear
that's
me.
better. They can hear me now. I said before we started this, I haven't checked the audio levels. I bet I fucked something up.
But man, it's sorted. It's sorted.
It's sorted. It's
We go.
working now. They can see us. They can hear us, or they could see us anyway. But what was I doing? Yeah. Okay, that's it. Now I can see the chat. Yes, I was muted. Isn't that good? Hi everybody, and welcome to the show. With me is wonderful Conspiracy Catz, who's already said hi to you, but I hadn't. As I was saying, we were going to do this last week, but I couldn't because I was away. It's great to have Catz here, though, and I'm sure you guys in the chat will love to pick at his brain like you love to pick at mine. But don't pick too hard because his brain's really important to the community. So really don't.
I don't know about that.
Yeah, I was talking to Catz before because he actually sent me a message earlier and says, "Is there anything in particular you're going to talk about, just so in case I have to look anything up?" And I said, "Well, one of the things I think would be nice to talk about is standard candles, because as it applies to when we are debunking like flat earthers or young earth creationists who want to talk about the universe being young or small, and why standard candles are important to that and how they actually work." Because it's an interesting thing that people go, oh yeah, they're explosions, but how come all these explosions we know are basically the same? So why are they the same? Why are they the same measured relative brightness for the distance they're at?
That's a yeah. That's a really good question. Although when we talked about standard candles, I had Cepheid variables in my head, which aren't an explosion.
No, they aren't.
You know what?
That's a different standard candles. I was thinking Type 1A supernovas, and I think I actually posted that. But Cepheid variables are another really good one, and it's a very similar reason as to why we know that they are things. But why don't you go with Cepheid variables, and then I'll talk about Type 1As.
All right. Well, a Cepheid variable star is a star that its luminosity varies with time, and over like a predictable cycle. So maybe over a 7 to 10 day cycle.
Yeah.
Some are a little bit longer. It will get brighter. It will get dimmer. It will get brighter. It will get dimmer. But the period that it changed its luminosity over is linked to its absolute magnitude via something called the period luminosity law. And I forget the name. It was a female astronomer that did a lot of work on this. Actually,
Yeah.
it began with a H. I can't remember her name. I'm going to have to Google that, or maybe someone can.
Yeah.
But essentially, the period luminosity law will tell us specifically how bright, at its brightest, one of these Cepheid variable stars will be. And then if we know how bright it is when it's a set distance away, we can use a different equation then, which is, I forget the name of it now, but I can tell you the equation. It's log 5d equals the apparent magnitude plus the absolute magnitude plus 5. But essentially, the further away that star is, the dimmer it's going to be.
Yeah.
And then we just compare, how bright it should be to how bright we actually see it, the apparent magnitude, and that can sort of tell us how far away it is. But the question of how do we specifically know how bright it should be is derived from the chemistry of the star, the physics of the star, the makeup of the elements it's got, the type of fusion that's happening at that time, which we get that information from, various different types of spectra, etc. But that's a little bit above my head for that bit.
Yeah, because the different compositions of the star will change the brightness within the star itself, because they'll burn it changes slightly the brightness of the star as as it goes, as well as, of course, the size of the star, because the size of the star, you've got different amounts of nuclear reactions going on, so stars will burn brighter and that. But the chemical elements in how pure a star is, so its level of metallicity, that's the word I was looking for. Why would my brain not remember that? The level of metallicity in the star also affects the perceived color of that star to a small degree. So you can also get an idea from that, with the brightness that they will achieve at their utmost brightest, because set of variables can be all different types of stars, but so it's not just one. I mean, it's a particular type of star because it's a separate variable, but it can be you can have larger stars and smaller stars. So you could have a star more like ours, or you might have a blue giant that's also a separate variable because of the way that it changes its brightness over time. Generally, most Cepheid variables, I believe, are older stars, so they generally actually are the largest stars anyway, because they're more likely to fluctuate towards the end of their life, especially as their metallicity has changed. So, but regardless, it's and the equation you were talking about, which I also cannot remember the name of it, so that's really annoying. And Dave's just giving you the name of the woman, Levitt.
Who was it? Oh, Levitt.
Levitt.
Oh,
yeah.
yes.
But yeah, I also cannot remember the name of the equation either. But I'm sure Dave's going to tell us from the chat.
Kicking myself. Sorry, go
ahead. But that same equation is the one that's used for Type 1a supernovas because we know what the apparent brightness of a Type 1a supernova should be, so we can use the how bright we actually see it, its apparent brightness, compared to what we know its brightness should be to determine the distance that it actually is from us. And we know the brightness that Type 1a supernovas are because they're all white dwarfs that are gathering more mass until they hit the Chandracroft limit and nova. So once a white dwarf gains back to a certain amount of mass, it becomes unstable and will form a supernova. So if we know there's a white dwarf somewhere that's gathering mass, we know one day it'll have a supernova when it reaches this limit, and the brightness of that will be within 10% of a known brightness level. So there is an exception to that, though, that was discovered last year by a group in Australia at the ANU, that most of them will supernova within 10% of that level. So just usually before they actually reach it, so from 10% below to the level. There are a small minority that can actually nova at a lot higher level, and that's because instead of getting their mass by dragging it from another star, it's when two white dwarfs collide. So an
actual collision, not a slow
build up, but when you've got two white dwarfs that are orbiting each other and their orbits decrease, they will eventually collide, and that will cause a supernova. And it can appear to us from a distance to be a Type 1a. I don't know that they're actually calling it a Type 1a, this particular one, but we have believed they were Type 1a's in the past because they give off a similar chemical signature that Type 1a's do. Because, of course, it comes from a white dwarf. So we know what the chemical signature is of these explosions, so we can know that it is a Type 1a supernova, except for in this case. And, of course, these explode with a mass that's double what that Chandracroft limit should be. So they explode much brighter. So we think they're closer, but they can actually be a lot further away, and we need to know what they are. But fortunately, rotating white dwarf stars that are getting closer and closer and about to collide and explode also show up with gravitational waves.
So there's that extra thing to look for them.
So if we see a Type 1a supernova and we've seen gravitational waves coming from that location just before the Type 1a happens, we know it's not a normal Type 1a supernova, and we can adjust our calculations based on the fact that we know there's a whole heap of extra mass that was in it. It's still not as accurate as a normal Type 1a because I think the percentage range for it can be up to 20%. So that's an awful lot of difference as far as the extra distance. It could be away or closer to us depending on the extra mass. of the two white dwarfs that collide, but it's still a usable figure. I mean, and regardless, it's still giving us figures that are in the billions of light years away. So we know from this that our universe is incredibly big. We also know that it's expanding, because we can see this, and then we can see the red shift from those stars. So we know how bright they were. We know the red shifts from them. So we know that they're moving away from us. It is really fascinating to know that we've also discovered that the universe is not expanding at the same speed in every direction.
Yeah, that is curious, isn't it? And I'm not, I know nobody's got a solid answer for that and a solid reason for that. That to me is fascinating. The whole idea, the whole idea that the universe should be accelerating in the first place, to me, is absolutely fascinating. But what have you heard as the reason for, like, possible reasons for why it's not consistent?
See, I find a lot of the papers that are written on it. I mean, the figures are known. We know it's not consistent in its level of expansion. There are a couple of things. Just because the matter that's towards the edge of our universe is being affected by our visible universe, not the edge of the universe. Our visible universe is being affected by the mass of matter beyond what we can see. That is within that field of gravitational. If there is large enough masses in certain areas outside our universe, stuff towards the outer edges of our visible universe could be expanding at different rates depending on how much matter is beyond that. And we know the universe isn't completely symmetrical in its distribution of matter, so it is conceivable that there's large galactic clusters that we can't see that are beyond our visible universe that are causing areas to expand at different rates. So that's a possibility. It's also possible that perhaps the way that dark energy works with expanding the universe isn't actually consistent across the universe. And depending on what exactly dark energy is, and perhaps that's got something to do with the way matter interacts with dark energy in and of itself. So there could be a nature of the universe that means because there's more, because of the way matter's distributed, it changes the way that dark energy actually affects it in certain parts of the universe, and that creates a different range of expansion. But it's one of those beautiful things that we don't know, and I love things that we don't know because it just means there's more to find out. So I look forward to papers in the future that talk about this and maybe come up with some solutions to it.
Well, that's what science is about, isn't it? And I think a lot of conspiracy theorists, they seem to think scientists pretend to know everything, and then as soon as a scientist says, "Oh, we don't know that," they'll jump all over it and say, "Oh, there we go, science is wrong."
It's the god of the gap in gaps in the form of you're trying to point out that a scientist is ignorant because they don't know something. Almost, it's the same sort of thing. A Christian will use it as god of the gaps. A flat earther will say, "Oh, science is ignorant," and yeah, so the Earth is flat. You don't know this one thing, so the Earth is flat. Yeah, but we know all this other stuff that says that you're wrong.
Yeah,
the bits
that stuff we're just completely not talking about.
The bits that we don't know don't prove you. And
oh, brilliant!
Brilliant. So, I find that really fascinating. That that they think it's a handicap for us if we don't know something. And yet, you and I as lay people and people with qualifications will go, "Hey, it's awesome. We don't know something. Let's go and find out about it." And that's how I feel about it too. It's like I want to know now that here's something we don't know. Let's find out about it.
Yeah, and that's the exciting part, isn't it?
Yeah,
that's absolutely the exciting part. But they use not knowing as almost a badge of honor these days. They've gone from flat earther to globe denier, and it's almost a badge of honor to say, "Well, I don't know what shape the Earth is, and I'm not claiming to. Therefore, I'm the intellectually honest one." Well, actually, no. Because you're ignoring all the science that tells you what it can't be, and it can't, it can't be flat, it can't be triangle shaped, it can't be a square shaped. But I'm going to say, so going back to the supernova before and knowing the brightness. Now, again, I'm just going to try and apply what we teach at school about this, because I don't really know like how they specifically know how bright that supernova is. But is it? I'm just guessing. Tell me how close I am. Is it a case that because they know the mass of the stars, they can gauge the mass? Is it? Do they look at the type of fusion that's taking place? And because we understand how much mass is lost in each particular type of fusion, they can use that E equals mc squared to predict the energy that's given out. And is it based around that?
No,
or is
well,
it,
in a general supernova, in a normal supernova where you've just got a star getting to the end of its life and exploding, you're not going to be able to tell exactly how far away that is by the explosion, unless, of course, you've got a very good idea of the mass of the star that exploded. So that does make it really complicated. But for type 1As, we know it's a white dwarf to start off with, and we know that's a white dwarf accreting matter from somewhere, or suddenly a couple of white dwarfs coming together. So in this case, we know it's been accreting matter and getting larger on its surface. So the mass from the other star that it's dragging matter from is accreting on its surface. Now, whilst white dwarfs can have a small range of sizes, they are generally all within about 10 or 15% of the same size of each other, which is a really good way to start, especially when you know that Chandrasekhar limit. Then that's the Chandrasekhar limit is how much matter the star can pull onto itself before it can no longer maintain that mass on its surface. So at that point, it will start to fuse the matter, and then you will end up with a you'll end up with a type 1A supernova. So that at that point, the star becomes no longer stable. So we know that we're starting off with a mass of X amount, and that Chandrasekhar limit has to be within a certain amount. So we know how much mass is in the explosion. If we know how much mass is in the explosion, we can calculate how bright it should be. And then we can know from how bright it appears to be, how its apparent brightness is, how far away it is. So it's not a case that we know how that all these stars should look when they explode, but we know specifically how this kind of star should look when it explodes. And because most of the mass of that star is going to be from the white dwarf remnant, there's a telltale structure to that supernova in the terms of elements that are in it that lets us know what type of explosion it was. So we know that it was a white dwarf exploding. Because we know it was a white dwarf exploding, we've got a damn good idea that it was because of the Chandrasekhar limit, and that was why it happened. So therefore we have a reasonable idea of what the mass was to within about 10%, so we know how bright it should have been. Which gives us a great way of judging its distance to within a certain degree. But that certain degree might be like 10,000 light years over a couple of billion light years away. So it's a minor amount in the scheme of things compared to the vast
an astronomical scale. You're not that far out.
It's not a huge order of magnitude that you're out in the distances. So if you get a type 1A supernova in a galaxy, you can be pretty sure within, probably less than a billion light years how far away that galaxy. It will probably be less within a million light years of how far away that galaxy is. Obviously, the further away it is, the less accurate that becomes. But from the point of view of knowing that the universe is bloody big, it's it's a moot point, really. I mean, it's like one of the things that often people don't understand is the universe is 13.8 billion years old. How can we possibly say that the universe is 96 billion light years across, the visible universe? And of course, the answer to that is the universe has been expanding ever since it started, and expands faster than the speed of light. So the most distance light we see from the most further stars, which are now 96 billion light years away, weren't 96 billion light years away when that light started. They were 13.8 billion light years away. But they are now, because of the expansion of the universe, that much further away. 46 billion light years. 96, 46. Yeah, I'm not sure if I got that right.
We A level, which is really my kind of like limit when it comes to sort of astronomy stuff. Yeah. But at A level, we'll look at using Cepheid variable stars to calculate the distance that they are, and the redshift that you mentioned before to calculate how the speed that they're moving away. And when you plot those on a graph, of course, you get a lovely, you get a lovely straight line, pretty much. And the gradient of that can tell us that the age of the universe. And the thing is that the fact that it does form such a lovely straight line when you're looking at it shows that our calculations aren't giving us random results. We're not getting random. It's exactly what you predict from a huge explosion.
Yeah. So we know expansion.
Yes, expansion. Yeah.
Don't say explosion. That
right.
That confuses them. Because I mean, the universe didn't. Big Bang is a misnomer. The universe did not start with a bang. It started with an explosion. Oh no, an expansion. I said explosion. I did it too.
Expansion.
An expansion. A very fast expansion.
Oh, brilliant! But yeah, no, we.
I'm very quiet apparently. Yeah, that's probably because I'm a long way from my microphone and need to shift in closer. Because I tend to do this thing and move to and from my mic. I need a lapel mic, so I don't do that.
Yeah, am I loud enough?
Where is he? I am going to... Chadwick Haller asked us a question in the chat, and he's complaining that I haven't answered it. So I'm going to send Chad a link, because like you, he's a science teacher.
Oh, cool.
And we'll see if Chad wants to hop in, and he can ask it himself. Where are we? Back there. So, Chad, sending you a link if you want to hop in. So yeah, I mean, whilst we were talking about that, we were also talking about gamma ray bursts, or fast gamma ray bursts as well, which is another one of those things where we were talking about there are things that we don't know, and it's exciting that there's things that we don't know, and gamma ray bursts are one of those things. We have lots of candidates for why they are.
We do.
But we don't know for certain exactly what causes them. There's lots of ideas. One of the things is Wolf-Rayet stars, when they get towards the end of life. And Wolf-Rayet stars are large stars that spin very, very fast. So when they explode, the amount of magnetism that there is within a star that's spinning that fast is enough to funnel all the energy very much towards the poles. So then you get that large amount of the explosion coming out from the poles. So you can get this gamma ray emission from the poles. That's one possibility. Another one is a fast feeding black hole. So if you've got a black hole that's taking on a very large amount of matter to consume and pull into the accretion disk, then that may cause it to release a gamma ray burst. There's even concepts of certain magnetars can pull in matter around them in the similar way to the accretion on a white dwarf, and then it basically funnels it out through the magnetic fields, but it has to accrete a certain amount of it before that happens. So there's a lot of really interesting ideas as to why fast gamma ray bursts can happen, and it's quite probable that all of these things can cause them. I mean, we're pretty sure Wolf-Rayet stars are a source, and the other things could be too. But we know there's been gamma ray bursts that couldn't have been Wolf-Rayet stars because there was no supernova that was attached to it. So
it's the same with magnetars. Magnetars started off as being the favourite, didn't they? For like the favourite contender, and I'm kind of like semi-aware of the explanation as to how that happens. But I know again they fell out of favour because they started seeing these bursts coming from places and types of galaxies that shouldn't be old enough to have magnetars in them. But there was. What was that chime detected not so long ago, which was something from within our own galaxy, which suggested very strongly that magnetars could be a source of this. It does seem that there are multiple different
sources.
They seem pretty certain now that magnetar, could definitely be one of them.
Well, we know there are repeating radio wave emissions that some of them emit gamma ray bursts, which are most likely magnetars, because there's really nothing else that can do that will give fast radio emissions that are regular and as at a close range. I mean, we know that we can get that from black holes in quasars from a distance, because it was one of the first radio signals that we detected in space that we thought could be little green men.
Yeah.
Because they're so regular. Spinning pulsars as well was another one that we thought could be little green men because the spin of the pulsar makes a regular emission. So there's lots of things like that can do things like that. But magnetars are a good one for this because there's lots of ways within the way their magnetic fields work, and if they're in nebula that they can accrete matter from where they can emit X-rays as well. So not X-rays, gamma rays. So as a regular gamma ray source and as a fast radio emission source, magnetars are definitely one of the leading candidates for that. But we honestly, it's one of those things. We have candidates, but we don't know, and it's beautiful that we don't know. It'll be even more beautiful when we do know, when we can say definitely it's this. Because...
Well, I hope one of them is the aliens. I hope one of them is contact. Yeah, that'd be great. But I know that doesn't sound. That
doesn't sound too sciencey, does it? When you talk about aliens. I mean, my personal take is we definitely have aliens. There are definitely aliens out there. Are there intelligent aliens within our own galaxy? That's probably less likely. Just because there's people talk about great filters, which are the things that could stop life from developing to the point of a sentient life developing to the point of having technology where we could discover them. And there are an awful lot of probable filters. I mean, for one thing, we have gone on the brink of nearly killing ourselves that many times that, and we know natural disasters cause mass extinctions very regularly. And if there was one coming our way, we wouldn't be able to do anything about it. And we're fairly advanced, but we're not greatly advanced. We can't stop a natural disaster. No. And these things are quite common to wipe out life as it's evolving. So, plus you've got the fact that we're not even sure exactly what's required around star for life to form in the first place.
No, I mean, obviously the laws of physics say it's possible because we're here.
Oh, we're here,
But I don't know if you get it where you are, but there was a program here, and we're going back about 20 years, but it was a hell of a program with a guy called Tony Robinson. He narrated it, and he's the guy who plays Baldrick in Blackadder. You might know him.
Oh, yeah, I know Baldrick.
He does. Okay. Oh, hi, Chad.
Hello.
How are you doing?
Not too bad, and yourself?
Yeah, very good, thank you. Very good.
So I had to step out for about 2 minutes grabbing a coffee there. Did you answer my question, Jen?
No, I haven't. I thought you could ask it yourself. And I'm trying to...
I wanted to know how you guys would handle one of the most ridiculous questions that I've ever gotten as a teacher. How hard would you have to slap a chicken so that it's cooked when it stops?
Love it. Oh, well.
So solve it. How do you do it? You got...
Okay, well, what we need to know, I would say, is we need to know the mass of the chicken. We need to figure out the energy, the cooking of the chicken. I'd need to look at the bond energies in the protein molecules and how they change when they're cooking.
Oh, okay.
Exactly how much energy. If I know the mass, if I know the bond energies of the chicken, like before and after it's cooked, I know how much energy's got to go into that chicken. But then that gives it the minimum energy for the slap. But how do we get the minimum energy? Well, what's that? Work done is force times distance. So how hard would you have to hit it?
Well, we assume a slap distance of 1 meter. Just
so the chicken
that's about 1 meter. Well, if you swing your arm after 1 meter, it's just follow through. There's really nothing there.
But if we know how far
distance
the chicken has gone, we've got to then deduct the energy, the work done into moving the chicken from the energy from the original slap, because that energy can't then go into the molecules. So it gets very complicated. What I'd have to do is staple that chicken to a wall, hit it, get more of that energy, bang, through the neck.
Spank that chicken.
And then I'd get a rough estimate from that, and then I'd have to maybe double it, treble it, quadruple it, because obviously you're going to lose a lot of energy. But that's how
surely the molecular integrity of the chicken would fail before you actually cooked it.
Yes.
So you're okay. See, this is where it gets interesting, because in order to slap the chicken such that it's cooked and not just mashed chicken, you can't really do that slapping chicken to the wall experiment, because that may not be enough to cook it.
So
that's why I was interested when you started talking about cooking. You started talking about almost a certain degree of protein degradation in the food rather than going for heat capacity and internal temperature. So it's kind of, I like the way people's minds work. That's all.
Yeah.
No, heat capacity crossed my mind, but if you're going to cook it, that's a chemical change. So that's what I want to think of specifically, the difference in bond energies before and after.
Well, you can also go with if you're talking about cooking in that sense, then you can go with a ceviche or something like that, where you just kind of put it in a nice vinegar or a citric sauce, and it just kind of cooks without heat. So at that point, you just have to slap it into a thing of lemon juice. So
yeah, there we go. Let's do
it's
that.
a non-question at that point.
Well done.
Now, what the nice thing about these is that because they take out all the innards, it's pretty much uniform in terms of its thickness and density and all that. Because you're not assuming, unless you're taking a live chicken, in which case you guys are monsters.
In my head, I had a live chicken. I don't know.
Yeah,
just smacking all the feathers in the head are left behind, and just the.
I'd imagine it'd be too difficult to staple a live chicken to the wall.
Yeah. I still have that visual in my head of you just spanking a chicken stapled to the wall.
Bad chicken.
Good morning. This is my first copy.
That's got a very different meaning in the UK. Spanking a chicken. It's got very different.
Hey, no judgment. Everybody's got a thing. Everybody's got a thing.
Oh my word! Brilliant. Love it.
All
What a
right.
great question, though. Those questions are great for thinking.
Where I get those questions from is back when I was fully employed and whatnot and had my own classroom. If I was ahead of schedule, I'd try to take every Friday or every second Friday and just say, okay, you guys have been forced to learn a bunch of stuff that you never asked for. So what do you guys want to know? Just ask me questions and just get questions from the students. And if you don't know, just show them how to research stuff, Google stuff with them, watch YouTube videos. It's a great experience. Yeah. And it gives something to students to look forward to. So they kind of like do during the week. They're like, guys, stop screwing around. That way we can mess off on Friday. It's like, yeah, I like this. So little thing.
I like it. Yeah, that sounds great.
So now Catz is going to go and ask his students that same question about the chicken.
Yeah. What a great question.
It's a good question.
You see, in my head, we have the chicken, and you slap it, and at the point, just initial velocity, negligible cooking at that point. So I just assumed the chicken would hit the ground and start. I assumed contact with the ground and a steady rolling. That way you can even cooking of the chicken, and an effective coefficient of friction, which would be relatively small because of the rolling action, but you could still do the thermodynamics necessary. So that's the way that I did it.
But I also probably need to hit a large hill with a big slope, though, because otherwise the chicken's not going to keep rolling.
And these are the wonderful things that I love about. Well, no, because the friction will slow it down eventually.
Yeah, exactly.
Now,
so you need a bit of a slope. Over
you might need a car distance. To get. Yeah, you might need a car to get to your chicken, but I mean, at the end of the day, you could still. But some of the students are like, well, in order to get it more uniform, you'd have to, somehow get the heat everywhere. So how do you? And then they start thinking about how to enclose the chicken in something, and it just gets those conversations going, right? You just start seeing them engineering and solving problems, and you're like, okay, this is fun, and nobody has any homework, and it's wonderful.
Oh, because you don't have any marking to do. I love that.
Yeah,
that's what it should be.
Oh yeah.
Now,
kids will remember.
Somebody asked a question earlier about why on earth would the world need an ice wall if there was a dome?
Ooh, good question.
That's a good question to ask a flat earther, isn't it? Because if there is this big dome that keeps all the atmosphere in, surely it could keep the water in.
Well, in that case, the dome would just be made out of ice, and the ice wall would be the dome touching the firmament. I mean, that's a non-question, isn't it?
Yeah, but...
No, I'm not saying that's the answer. I'm saying that's consistent with the logic.
But surely the ice dome would melt because of the sun inside the dome. So.
Well, you're assuming the sun is the sun is hot, isn't it?
Yeah. I think that's a safe assumption. I think they'd all agree with that.
Yeah, the sun is hot. Okay, so. assuming a cold sun.
Assuming a cold sun, yeah.
Yeah.
Oh, no, what it is the cold light from the moon balances the warm light from the sun and stops the dome from melting.
That's why it's kind of clear.
I wish I had said that. Some flat earther is going to say
this is why
that.
you have that nice clear ice. That's why you get that clear ice. It's that constant melting and recooling. You get all the air bubbles
keeps
out,
it nice
right?
and flat, yeah.
You can't see through the ice on the ice wall because, I mean, that hasn't been cleared as much. It hasn't gone through the cycling.
And of course, if you have a few little bits starting to melt, that could explain stars. Because you get a bit of more diffraction of the light in the...
Well, unless the heat somehow distributes itself over the dome and then kind of collects into places that we associate as being stars.
Stars, yeah.
Yeah.
Hmm.
How deep down the rabbit hole you want to go?
Me.
I can talk a lot of shit.
This is the problem
I can talk
when
a lot of
people who
shit.
actually understand science want to try and make the arguments for the flat earthers. We tend to do a better job than they do.
Oh God, we can for sure.
Okay. Full disclosure, I have firsthand done the Cavendish experiment and traveled the world using a sextant, literally from Hong Kong to North America. The world is round. I'm just talking shit.
Yeah, same.
So this is that little bit that people can use, and later in my future, when somebody uses that clip to say he believes in a flat Earth, like I can use afterwards. He said. So I've got to cover my ass. I'm gonna be famous someday.
Definitely. Oh, brilliant.
Definitely. So what's your thinking on standard candles, Chad, and gamma ray bursts? Because we were talking about those. So.
You were. It's been a while since I've kind of looked into any astrophotography. Sorry, not astrophotography.
Astrophysics.
That's why you can see where I'm kind of going a little more artsy-fartsy these days.
Yeah.
But as far as I know, when you're talking about essentially the conversation you guys had, I'm more or less completely on board with. The only thing that I would add, and I'm not sure if it's 100% true, but it's kind of headcanon. Basically, one of the reasons why Type 1A supernovas are so standardized is because when you're talking about how stars collapse and you end up with the white dwarf, the neutron star, black hole model, essentially the type of explosion that results in supernovas, the smallest ones, these Type 1As,
Type 1As,
essentially have a fixed chemistry, because if that star was either bigger or smaller, it wouldn't have been such to explode in that way. So it's kind of a Goldilocks zone for a type of star that explodes.
Yeah. Which is why we
So
know
it's
they're all within 10% of being a certain mass, and they all have a certain chemistry. So we know exactly from the supernova from the light from the supernova remnant, exactly what type of supernova it was.
You can kind of make an analogous thing to calling them super. When you say Type 1A supernova, you're kind of saying uranium, but it has different isotopes. Most of them are like this, some of them are like that, and you kind of have a range sort of thing. But it's not discrete, but that's kind of the thinking of it.
Yeah, which is why we have that problem when we end up with what look like Type 1A supernovas of two white dwarfs circling each other and colliding and then causing an explosion. Yet the explosion is a lot larger than what a Type 1A normally is, because there's a lot more mass involved. So, but you end up with the same type of remnant because of what the material is. So that's what has been the confusion. So we've actually had to go back and look over some of the earlier Type 1As that were out there and figure out which type they were, so we could know if our distance measurements were accurate. So,
I'm interested to know, when you started bringing that up, I started thinking about how many potential 1As actually have to be reassessed. And based on the fact that what we know about 1As and standard candles was basically one of those fundamental building blocks for Hubble, when he basically said, hey, the universe is expanding. It's kind of a big deal. So stuff might change in terms of the numbers. So we'll see.
They only figured out this other one last year with... and the reason they figured it out was because of LIGO. Because we detected the gravity waves before the supernova happened. And hang on, it's a Type 1A. That doesn't make any sense. Oh, crap. We've got a problem.
Yeah. I remember seeing all the little videos of the beautiful little... gravitational wave. Yeah.
Okay, we've got a problem because we've detected a gravitational wave, and there shouldn't be for a Type 1A supernova. but we've got one.
Yeah.
And so it's got the chemical remnants of a Type 1A, but it obviously isn't a Type 1A. So now which other ones weren't, and we have to go back and look at it. And we can get an idea of that by how large the expansion has got of these Type 1A since it has happened, because of the amount of mass.
It shouldn't change too much.
Sorry, the density of it, not the size of it. It'll expand at the same rate, but the density of it will be different because of the amount of mass.
Yeah, assuming like a fixed proportion of these things have been miscategorized, it shouldn't change too much in terms of the Hubble's work. But now that I'm thinking about it, but it's interesting.
They're going to have to go back and look at it. It was only a year ago that they found this out, so. It's been a while, so
because this could only become significant if hypothetically in the early universe this anomalous type of explosion was more common than the ones we have now, and if that is true because of interactions between first generation stars, I don't know. I'm just spitballing, but that would be what I would have to see in order to go down that road. If that makes any sense?
Yeah, no, it does. That makes perfect sense.
For coffee one on a Saturday morning.
Oh, it's good. I always like your input, Chad, because you make me feel silly.
You have to be silly. We need some. What's going on in the chat? Do we have any stupid questions?
We probably do, but I hadn't been paying that much attention, to be perfectly honest. Rather than scroll back through them, if you had a question from earlier that we haven't answered, and you'd like it answered, please put it in. If there are a couple of other people who wanted to hop in, want to hop in the chat now, please feel free. Those who've got the two other people who've got links, if they're there and they want to hop in, please feel free to hop in and either ask your own question or get ready to have your brains picked as well.
So
I'll
sorry, go on.
I was just going to make some noise. Go ahead.
No, well, I was just going to finish what I was saying just before. I was talking about Tony Robinson documentary. We'll leave that there. No, well, I was just.
Yeah, Jenny.
Hi, Jenny.
Morning, Jenny.
Hi.
I will. Yeah. I gotta get
you guys are really.
You, Jen.
You guys are really talking way too smart for the chat. Way over the head.
I was talking about slapping chickens. We want to go back to chickens?
No, but I had a question. I was thinking, Catz, given your history and knowledge of the Nate Thompson theory of thermodynamics.
The Nathan Thompson theory, I like that take on it.
Do you think it possible that since we're able to use the sun to harness energy to the point of utilizing its heat energy specifically for keeping ourselves warm in the winter now that it's winter, couldn't we also harness the moon's cold energy to give us air conditioning in the summer?
It's too busy doing the ice wall. Too busy with the ice wall.
I think using Nathan Thompson. So possible. Oh, brilliant. Yeah, I think using Nathan Thompson's theory of physics, I think anything is possible. Absolutely anything. So let's go for it. I think we can use my banana to light up the streets of London for the next 20 years. Why not? Let's do it. Yeah. Oh, he's suffering lately, isn't he, with all that prank? That's not going to go away anytime soon, is it?
I don't know if I'm familiar with all the drama because I tend to stay out of it. But
you haven't seen the guys in chicken suits?
That was brilliant.
Duck suits. Be fair.
Duck suits.
It was brilliant.
Sorry.
There's a big YouTube channel called Reckless Ben. I think he's got about 80,000 subscribers, and his YouTube channel is pranking people. That's what he does.
Okay.
And they contacted Nathan Thompson. They met with him, and they went dressed in suits as ducks or chickens or whatever they were. And that didn't set alarm bells off with him. But they told him that they tried to do an experiment to prove the Earth was a globe, and ended up proving the Earth was flat. And basically they filmed it like a little mini documentary. They're releasing it in little segments and videos. And Nathan Thompson was just for everything stupid that they said, that they did, he just couldn't see he was being pranked. The whole thing he just fell for. Even to the point where, as afterwards, when people said you've been pranked, before Reckless Ben actually said, "No, we have pranked you," he was saying, "No, you don't know what you're talking about. That they were real. They've really proved that flat Earth. You know, just gone."
Some people are just thick.
Yeah,
Well,
so he
it's
is
just
particularly
amazing.
thick. He really is particularly thick.
What amazes me is how small people's worlds are. Like, people have it's almost as if they still live in a feudal village in medieval France somewhere. You know, they haven't been more than 2 milestones down the road.
Probably some of these people have. They've been on
They need to
planes
start
and flown.
thinking bigger.
Some of these people
What's that, sorry?
have jet set around the world, and they still think the world is flat. You know, they've
But
experienced time zones, and they've...
These are the people who, when they travel, eat at McDonald's. And you can find McDonald's everywhere in the world. Everywhere I've been, you can find a McDonald's. These are the people that travel, and then when they get there, they say, "Let's have a Big Mac," and then they complain about the quality of the food.
Yeah.
It's a completely the wrong kind of person. Now, as a Canadian, I will put a little bit of a disclaimer here. Our national identity is in a big way not American, so you'll hear me bashing them a little bit. But it's kind of a national pastime.
You'll only
coming
upset Jenny.
coming from a
You'll only
coming
upset
from a,
Jenny here, and the rest of us aren't Americans. So.
coming from a country that national dish is gravy on top of French fries. I don't know how much talking you get to do.
I'll have you know it's a beef gravy on top of yes, it is fries, but you need a specific type of cheese curds. They've got to squeak. If they don't squeak, it doesn't work.
Well, that just means they're fresh. I'm from Wisconsin. We know squeaky cheese curds.
We actually have a couple of questions from the chat now. So,
delightful.
Now, Microraptor asks, here's a couple of stupid questions for us. Is the Earth actually flat, and how much is NASA paying all of us?
I'm currently sitting in a shed having a smoke, so
yeah, I'm not being
this is what
paid by
NASA's
NASA.
paid for. Looks like Catz has got a couple guitars out of the deal.
They're just painted on the wall. That's all. They're just painted on.
You got paint?
Yeah.
Wow.
That's what we paint.
Garage.
It's the orange stuff that they aren't painting the fuel tank with.
Dave's the rich guy here. He's in a spaceship.
Yeah, that's pretty cool. That.
Nerdy Roden asked, how do we know the sun is hot?
No, that's actually a good question.
It is a good question.
Because all we know is that it tends to be hot when it's bright outside. Empirically speaking.
Yeah. We know that when it's bright outside, we can put things in it and it will heat up by a certain amount.
Yes.
And when you put it in the shade, it heats up less. So we can infer directionality to the heat, yes.
And if you're assuming you calculate the distance, you can then work out the inverse square backwards.
Well, yes, but you're assuming at that point there's still the assumption that the heat is coming from the sun, not necessarily from
I've got
the
a question
atmosphere.
For you. We cook things
the
with
direction of the sun.
microwaves, but is a microwave actually hot?
We could stick our hand in the microwave and turn it on and see what happens.
So we're using a form of electromagnetic radiation to heat something up. And the sun is just electromagnetic radiation that's being sent to us. So in that sense, is it actually hot? There is a temperature for the sun that we know of. But what's coming to us isn't effectively heat. It's a form of radiation.
William Herschel did a great experiment. You're familiar with his experiment that discovered infrared? He took a prism, essentially. He had his room blacked out, and he pierced a little hole in the window, and a ray of light came through. That's how he created rays of light in them days. Didn't have the ray boxes, and he passed that through a prism, split it into a rainbow, and then he measured the temperature of each colour. And he saw that as you go up towards red, the temperature gets hotter and hotter and hotter. And then he took his thermometer and he put it outside of red where he couldn't see any colour, and that was the hottest part.
Wasn't that meant to be his control?
I don't know. Maybe. I
can't remember if that was apocryphal.
Well, he might have. It sounds like a good experimental design at that point would have had a control on either side, plus a control without the dot at all. So you'd have to actually block it for control technically. But in principle, he should. He would have been just as surprised as the Rutherford experiment at this point when you see atoms flying back at you. It just doesn't make any sense, you know.
It was by far the hottest. It was.
That's really cool. I didn't know about that one.
That was significant because obviously he measured the room temperature elsewhere. He moved the thermometer then further on to different places and other places in the room, which I'd assume would have been his control. But essentially, that was like the first. So sorry, the question was, how do we know the sun is hot? Well, that is. Thanks, love. Thank you.
That's a good way to do it. Yeah, you're getting heat directly from the sun.
Yeah.
So essentially, you found the heat ray.
Yeah.
Essentially,
yeah. Heat ray.
Well, see,
right.
But what I disagree
the Martians
with on that,
came and
what I disagree about on that is that you can take, say, a bowl of water or an egg on the sidewalk in the heat of summer is a good one. Crack the egg on the sidewalk, and eventually it acts as though it's being cooked or behaves as though it's being cooked on the stove. Well, if the sun is able to generate that much heat, why aren't the clouds boiling?
In that particular case, the heat would be coming from the concrete, not the sun directly. So it'd have to be like an asphalt, typically, like something darker. So that would only prove that the ground gets hot during the day, not necessarily.
Then wouldn't it make sense that fog would boil?
It does. It disappears.
Yeah, it evaporates off.
Crap.
It burns off here every morning. I live by the sea.
I mean, heat is just a measurement of activity anyway.
Well, this is the problem. Your question was interesting about the fact that when you said, "How do you know is it giving off heat?" In the it's giving off electromagnetic waves rather than what we consider heat, which is movement of particles.
Yeah.
But you do count that. We still count that as a measurement of heat.
We do.
Well, yeah, because at this point you're talking about electromagnetic fields going back and forth, and what that's going to do is move protons and electrons around. So.
And
I'm heating up, just wiggling back and forth.
Up at this point that
Technically,
we're talking about forms of energy, and energy is effectively matter anyway, so we're talking about the same stuff anyway.
Yeah, but I didn't slap the chicken at relativistic speeds, okay? Let's just get out of that field.
Okay. Oh, are we going to go back to Santa from last night, are we? How Santa could... I had another thought about that, actually, that there is an entirely different problem associated with that, and it came to me when you were talking about he wouldn't be able to slow down to deliver the presents. Well, he wouldn't actually be able to deliver the presents at all because the
house. Go ahead. Sorry.
The presents would eject at relativistic speeds, and he would not be able to slow them down. He would actually be a lot better off ejecting the presents at relativistic speeds on their own little missiles and have them land at the right locations than actually him flying around. But even though it doesn't
systematically move every house on the planet in one night.
I want to see if Jen gets it. Go.
What
are you going to say, Jen?
That's where Elon Musk got his idea for the rocket landing, isn't it? He stole it from Santa.
Yeah. Of course, there is the entire other problem of things moving at relativistic speeds, and that is the radiation that builds up in front of the object that's moving at that speed would actually kill everybody on the planet. So, plus the friction within the atmosphere would also cause major problems.
Without even getting... I was just
what if
say, without getting into the atmosphere, without getting into general relativity, it falls apart purely on special relativistic grounds. Because as you think about it as a standard physics problem, you've got a chimney and you've got a present. Yeah. So the present's coming along at relativistic speed and has to fall into a chimney, right? It has to get between these two things.
Yes.
Now, here's the problem. Are you guys familiar with the standard ladder barn paradox?
Oh, no.
Yeah.
No? Oh, no. This is when, essentially, due to length contraction, when you're traveling at relativistic speeds...
I knew you'd be talking about length contraction, but I didn't know it was called that. Okay.
Yeah, so when you're moving at relativistic speeds, objects will just tend to shrink a little bit to an external observer. Reasons not exercise left for students. So if you had a barn that was, say, 10 meters long and a ladder that was 12 meters long, in principle, the guy with the 12-meter long ladder could be running at relativistic speeds such that I, in an external reference frame, would see both the ladder being less than 10 meters within the barn, which is 10 meters. So in principle, I could close the door and the latter would be contained within. In principle.
Mm-hmm.
Now, that is true, but what you then have to get into is the sudden deceleration, the reference frames, and essentially the fact that that's a nuclear explosion waiting to happen. But based purely on how it works on paper, things are weird. You can't really. Yeah. Anyway,
It's what if, which is
essentially every gift landing in a chimney would more or less be a nuclear explosion, is what I'm getting at.
Yeah.
Not only that, how do you actually get it in the chimney?
baseball.
Yeah, but it would be a small one. I mean, a Barbie doll is not that big.
If you hit a baseball, a standard thrower threw a baseball, okay, and the batsman hit it back at
At the speeds, yep.
Yes.
Yeah, at light speed, just under light speed, it would vaporize the thrower before it got to him.
Yeah, because of the radiation at the front of the.
Yeah. So basically, anything you ejected from the sleigh would be a path of vaporization.
The sleigh itself would be a path of vaporization.
No.
We're assuming that the sleigh can survive.
Santa gets a pass. Santa can
gets
break
a
the law.
pass.
He gets a pass.
Okay,
It's the chimneys that explode that's a problem for me.
Well, there's another problem with the chimneys too, to do with length contraction.
Unless chimneys are magical.
Is that
Yeah, but the chimneys
Chimneys are
aren't
magical.
relevant. The chimneys aren't relevant because you're already vaporizing the atmosphere by the time you get to the
But
chimney.
even if you don't, Dave, that whole concept of length contraction is also a problem because length contraction is also relative. So from the point of view of Santa and his sleigh, the chimney is contracted to the point that it basically doesn't have a way in.
But Santa knows that there are external observers who believe in him, and their observing and their belief are what allow that reference frame to exist, and thus it enters the chimney. Santa gets a pass. Back off. The chimneys are the problem.
How high above is Santa flying?
Doesn't matter.
Well, yeah.
Well,
How contracted is the chimney in a height fashion?
He'd have to be fairly high to get the dispersal rate necessary to cover an entire city in an instant.
I mean, neutrinos, when they come through the atmosphere, that they would see the things on the Earth as being millimeters high.
He would also have to start accelerating his sleigh the year before Christmas because if you're going to assume that he's going to accelerate at 9.8 meters per second, it will take approximately a year to accelerate to relativistic speeds.
Okay. Santa never slows down. This is how he always knows. This is where he gets his list from.
Because he's everywhere all the time.
You got to believe.
I think he's right.
All right,
I talk a very
let's go
convincing
back to
game
the
of strike.
Question, because Nerdy asked if we wanted to cook a chicken on the end of a great big long stick using the heat of the sun, how long would the stick have to be?
How fast do you want to cook your chicken? Because the longer the stick, the shorter the cook time in principle.
Well, 10, 15 minutes, I think, would be a good time.
Well, standard cook time's like 15 to 20. That's how you usually get the internal temperatures. I mean, if you don't know how to cook something, cook it for 25 minutes and you're good.
Is there at no point before you hit the sun is there enough energy delivered to something the size of a chicken? I don't think. I think you would need mirrors to create enough focus of the energy.
Well, yeah. See, because space is not a good. Is a better insulator than it is a.
Well, it's either going to be in the atmosphere or on the sun.
So even when you're close to the sun, the amount of energy you get is still by the square meter law for the rate of energy that falls over a given area. Even up close to the sun, you still. Because rays of light are virtually parallel. They become less parallel, obviously, as you get closer to the sun. But you're still only getting a certain amount of light from the sun actually hitting the object, even as it gets closer. So you'd have to get close enough to the sun that you were being lapped at by plasma as it came off the sun. In fact, you get better cooking from the particles being ejected from the sun.
What if your chicken was covered in tempura batter? Wouldn't that insulate and slow it down?
A little bit, yeah.
Insulate it so it keeps the heat in better.
Yeah.
You see, my concern about this particular question is because the original question was, if you have a chicken on a stick, how long does the stick need to be, right?
Yeah.
Okay. So if you take a chicken and just put it out on the sidewalk, it is not going to cook. And it is getting every wavelength from the sun, in principle, minus what comes to the atmosphere, but basically everything.
Yeah.
So that's not enough to cook the chicken. And this is where we have to go back to your chemical definition of cooking.
Of cooking.
You actually have to induce enough energy, like thermal vibration, to start changing chemical bonds and breaking those down. So at this point, we do actually have to do something with the chicken. So we're talking at least a few AU here. At least a fraction of an AU to cook this chicken on a stick with just.
I don't know. What if we? And I might be off here, because thermodynamics isn't my strongest point. Don't let a flat earther hear me say that. But if we look at the if we look at the Boltzmann equation, right? If we look at what the activation energy is that's needed for whatever chemical change is going on to cook the chicken, then to look at the Boltzmann distribution, we know that there are going to be an infinitesimally small number of those atoms or those molecules that are going to have that activation energy for that to happen. And as long as we have an input, a constant input of whatever that temperature is, then surely, I know the chicken will decompose first, but is it not just inevitable that if we give it long enough with that constant input of energy, that we are going to have that small
that's what I was
fraction?
trying to work out. If you put it on in the North Pole, if you put it somewhere where there is constant sunlight.
Well, the problem is the chicken acts like a black body. And once the chicken gets to a particular temperature, let's assume a space chicken, so atmosphere is gone. So once the chicken gets to a particular temperature, it's going to start radiating its energy off again. So this is why I'm saying we need a stick that's at least on the order of an AU.
But what about the
The
time?
problem with that is you couldn't have a stick the size of an AU.
Well, no, I'm not saying this is a good way to cook a chicken. I'm just saying for the solution to this problem, this is what we're talking about.
Yeah.
But what about the time it takes to get?
That?
What about the time it takes to get the chicken to the point of cooking and then retrieve it? What additional cooking time is that going to cause? Secondly, would it cool down? And secondly, given the nature of perspective, when the chicken's that far away, how would you be able to see that it's cooked, or would it have been gone over the curvature or something?
One of the interesting things about space is not only does it take a long time to warm something up in space, it also takes a long time for the heat to radiate off, because there's nothing for that heat to radiate off to. So it is conceivable that the chicken would not be completely cold by the time you got it back.
But this is where I was saying, as a black body, I'm not sure how much this chicken is going to glow, essentially. Now, granted, it's glowing in the infrared, but we still essentially have a hot chicken in the atmosphere. Maybe that's what our sun is.
A hot chicken in the atmosphere.
Yeah, it's a hot chicken just going around.
And we have to worry about when all the feathers are burnt off.
Yep,
that would be a really big
stars.
Chicken.
Really big. That's the Colonel's secret recipe there.
This is my creation myth. So what we have is a hot chicken going through space from the time I slapped it. And when I slapped the chicken, the feathers went over the dome.
Creating the stars.
Creating the stars.
In the nebulae.
And the chicken to this day goes around.
I'm wondering
as a warning.
Yeah?
I'm wondering if Catz is still happy he came on the show.
These are some of the best questions I've ever been asked. It's great.
I love having discussions when you don't have to defend something, because you can just go off the rails safely and just have fun. No flat earthers about. You don't have to worry about phrasing. It's like, all right, Santa's real. Believe.
Okay, so Junk Shop asked if the stick was long enough, would the atmospheric drag on the chicken at high altitude help to cook it?
See, I was wondering. I think you might be better to have a stick that spin round. Then you would be well. Before you got a stick long enough to.
Well, Moody didn't actually.
That's
say
another
where
question.
You were. If you were in orbit in space and you had a reasonably shorter stick and put the chicken out the window and dragged it along the atmosphere, that would cook.
It would,
Well,
but
no,
if you're in the high atmosphere, the density of the atmosphere is pretty low. So I mean,
Yeah, well, yeah, you'd have a reasonably long stick, but it would be a lot shorter
I
than going
think-
to the sun.
I think-
Although he was interested in cooking in the sun, but you could cook
yeah,
in the
I
Earth's
think
atmosphere.
Dave's onto something with this swinging chicken thing. So if you take a chicken and put it on a rope and you just swing it really fast, assuming you have 20 minutes to cook this chicken, so 20 minutes of rotation, you could calculate in principle what speed that chicken would have to go at with the drag to cook the chicken just on a string going through the atmosphere. Now it's probably going to be somewhere around Mach 6, but in principle it's possible.
Yeah, but will you be able to build a device that does that and still fit on the counter in the kitchen?
Well, it'll roll up.
Microraptor has a legitimate question.
Yeah.
Okay. What's the question?
Go on, Jen.
I don't have the chat.
I'm looking for it. It disappeared.
Which
what's
one?
a black body?
What is
Had
black
a legitimate
body?
question.
What is a black body?
Sorry. Catz, do you want to take it?
Well, a perfect black body is one that I mean, it's to do with how they radiate heat. It's going to have been a long time since, but a perfect black body is one that will radiate. Well, I mean, would we say 100%? Like, what? How do we define it?
Well, it's the other way. It absorbs all.
Yeah.
It does
Black
both.
body absorbs.
It does
Oh,
both.
so, yeah, but yeah,
Black
yeah,
body,
it will
I
absorber,
absorb
black body
100%.
radiator.
Yeah.
I was going to say, though, can we then say that it will emit 100% of the? That's where it should be.
Well,
Yeah,
not
it's going to absorb.
Eventually, yes.
Yeah.
So a black body is essentially, if you imagine something at normal mass,
Junk shopping. We've
He's
lost
gone.
you there,
at
Jen.
zero temperature, essentially you have no. Oh, am I back?
You're breaking up,
Am I
Chad.
back?
Yeah, you're breaking up a bit.
Am I back now?
Yeah, we can hear you.
No?
Yeah.
Okay. So, yeah, essentially, if you have something that's cold in space, it's just going to be completely black.
Yeah.
But as you heat it up, in the same way that when you take an old stove and start heating that up, it'll start off black and cold and then go red and orange and slowly get up to this white hot. What's happening is essentially as things are jiggling around and heating up, some of that energy is being given off as electromagnetic radiation, and there's a fixed spectrum towards that. So essentially anything that has a temperature is shining in some sense in the deep infrared, basically. And the hotter things are, the more energy they give off at higher frequencies. So when things get hot enough, then you can start seeing things like ovens getting red hot. Where that's where we get that phrase from. It's a red hot radiator.
Because a black body isn't necessarily black.
No, they never
Sun is
are.
the best black body in the solar system.
It's black in terms of the radiation it's giving off intrinsically,
Yeah.
which is to say that if you can see it, that's because light's coming in from somewhere else, coming into your eye. It itself is not radiating,
Yes.
despite what the moon does in terms of its coolingness. But because the sun in principle, the moon in principle is a black body as well, but we don't see the moon when the sun doesn't shine on the moon. We don't see it because it's black, basically. Now it's more complicated because of the atmosphere, but yeah. Does that answer the question? I suppose?
Pretty much.
Just everybody's
so.
satisfaction.
Well, my brain hurts, so it must be something important.
Don't.
Sandy asked if wouldn't the rope
My-
burn
my-
before it was done, talking about spinning the chicken on the rope. Doesn't have to be a rope, and it depends what the rope's made of.
We're assuming physics rope here. You can do whatever you want with it. It doesn't break.
Yeah.
Yeah,
It's a magic
I-
physics rope.
Good
I
for
have
Skype.
I have a legitimate question. Something I've always wondered, ever since I was a little kid and John Glenn went up. Okay, if they took a space capsule and they're bringing it back to the Earth, they always say that when it goes through the atmosphere, it heats up to such a degree that it needs to have a heat shield and all that kind of stuff.
Yep.
If you brought it through the atmosphere slow enough, would it just not heat up? And couldn't you just save
would
a
not
lot of
heat up,
money
correct.
and wait, do it that way?
Yeah.
The
Yes.
problem is we have no way to slow it down.
Well, we have the atmosphere itself. We can slow.
Well, and that's it.
They're talking about with one of the, I think, Starship. They're talking about skimming it around the planet repeatedly, slowing it down. Each time it hit the atmosphere, it would heat up a bit.
Well, that's
But
why
it
the
would
space
heat
shuttle
up.
was. Yeah, that's why the space shuttle was as big as it was and had the big black bottom. It was to slow it down so we could reuse it.
Well, to be fair, the space shuttle was also it needed to slow it down within a much shorter period than is necessary naturally.
Yeah,
the space shuttle did
but
not
I'm
want
just
to.
using it as an example of. But the thing is, burning up through the atmosphere is actually a good thing, and I say that because the atmosphere will slow you down for free. You don't have to carry fuel to do it.
Yeah.
So if you want to come down slowly, you either have to get hot and stay up there for a long time like the space shuttle, or you have to actively burn an engine to slow your descent and actually expend energy, which needs fuel. So, but if I just come screaming in and go, Geronimo, all that energy is for free. If I survive, bonus.
To a certain extent, an ablative shield is a form of engine. In that sense.
No, I would
not terribly directional, but
not.
It's not.
This-
I mean,
It's a means. It's a protective means that allows for a safe propulsion. It's more of a seatbelt.
yeah.
Do you know if
that's fair.
It will,
know-
it will
Chad.
come through the atmosphere no matter what. But without a seatbelt, you're not getting through it.
Do you know if Starship's proposed heat dissipation system has been tested?
Not to my knowlage, but it's.
I
Not
don't
to
mean
know
I
already.
know their one hasn't, but I meant in
I know.
other experiments previously where you have a liquid acting as something that dissipates it.
Well, what is the system? What do they do? What
They are
proposed?
going. It's going to sweat, effectively sweat. I've forgotten what they're going to sweat. Methane. Basically, they're going to cover the outside in methane and let it sweat out, and that's going to basically catch fire and run off and take the heat with it.
Essentially, heat loss through evaporation.
Yes,
Yeah.
basically.
You could use astronaut urine for that in principle.
Yes.
You get that for free. But they're doing that, you give up water. So it's a balancing act. But that brings up
I can't
thing
believe
about
that
this black body radiator.
I can't believe that system could work. You know,
This is why I'm asking.
Okay.
I've seen all the theory on Starship and how they're going to use it, but I've not seen any 70s, 60s experiments where they've done anything similar. Which most of the technology that SpaceX is working with is stuff that's been studied extensively. They're just putting it together.
Back in the day, we in building race cars and stuff, we used to experiment with different ways of cooling the brakes. It's important to keep brake discs from turning cherry red, and so we would try. At one point, we tried a water bath with spigots at each wheel to directly hit the rotor and to cool it down through evaporation. It ended up being not allowed
Dangerous.
because it made so much steam.
Yeah, I'd say. It's a
Nobody
death
could
trap.
see anything. But
Well, oddly enough,
we couldn't carry enough water to make it actually effective.
well, the thing with the coming into the atmosphere, they're hoping that as they start to evaporate stuff off, it in its own right will give kind of a Leidenfrost effect. So they won't be having to give it off at a rate that you would have to with water and steam, because there will be a gaseous layer between the oncoming atmosphere and the spaceship.
God, that's something you'd want to make sure you did test.
Well, I'm kind of thinking about this from a slightly different perspective, maybe, because I'm thinking about essentially the questions about the thermal stability of an object in space and whether or not you can live in it, right?
Yeah.
So we have the space station. It doesn't have any means of generating heat. We'll ignore all the solar stuff, but it doesn't have like a nuclear generator on it or something like. It doesn't have anything to heat it up.
But it has not losing much heat either.
Well, but what we can do is assume a more or less stable system, because so far it hasn't been a problem and I haven't heard anything about it. So I assume it's a non-issue in terms of heating up.
They have more of a problem cooling down than they do heating up.
Yeah, and that's what I was. So in terms of how they cool down now, what are they doing?
If I
we
recall
know?
correctly,
I
they've
don't-
got giant radiators on the side of the space station, but I could be wrong.
Because using
I think
if you think about the radiators that you typically see on top of like a computer CPU fan or something like that, these thin radiator designs, which is more or less a way of increasing the surface area so you can get rid of as much of this surface black body heat we were talking about as possible. I don't recall seeing them on the station, but this is not, again, it's not something I've looked into. I don't even know if there are technologies for that
they are
don't
definitely
require.
using radiators.
The space shuttle had a radiator system that dovetailed on the door, and when they opened the doors, there were kind of a radiator system. I thought that helped with the heat accumulation is going to be the bigger problem. Or I should say, dispersal of that heat accumulation is going to be the bigger problem of the two.
Yes.
Look at a building
absolutely.
in downtown, a skyscraper. They have to run the air conditioner in winter just because of the body heat.
Well, it's the biggest problem with basically every spaceship we've put up, and especially the infrared telescopes.
I don't know. I honestly don't know.
But wouldn't you still have an issue, even with the Leidenfrost effect, given the huge amount of heat that's involved with re-entry, even with a small barrier between there'll still be a passing of heat from one surface from that
Yes.
that area to the ship anyway.
This is where you've got the dissipating off the rest.
Yeah.
This is why it's a constant sweating process.
So I do. I mean, yeah. You'd really.
So I can see why they want
to test that. I'm not sure you could effectively do that. If you could actually, like Jen said, I'm not sure you could actually carry enough fluid to do it.
And that's the thing. And that's kind of why it makes sense to use methane, because methane doesn't. It basically sublimates like super incredibly fast. It doesn't sweat the same way that water does because it doesn't have the same heat capacity. But the problem with using something like methane is that it has such a low heat capacity, it can't carry away a lot of energy. So you're starting to get into this point where you need essentially this giant thermal, like essentially a pool of water that you have to somehow keep cool, that you run through the spaceship somehow.
The point is they've already got bucket loads of methane. Because that's the fuel.
And do you want to carry an explosive gas
They're replenishable
out in space with you?
No, methane is what they're using as the fuel. They're
where are
using
they getting it from?
they want to be able to get it on Mars.
Okay, you're talking about a Mars situation. Okay.
No, I'm talking about the Starship is being designed to run on methane because of Mars.
Okay, fair. I wasn't sure that was one of the design part of the problem.
Sorry.
Go on.
Go.
No, sorry, go on. I was only going to ask a question. So
Go on.
Go for it. I had nothing intelligent to say.
I can't see the advantage of that system. Obviously, there has to be one, otherwise you wouldn't be looking at it. But I can't see the advantage of that system to keep it cool on re-entry as opposed to the traditional method. So why are they trying something
because they want it reusable, 100% reusable.
Because they want it to be reusable. Okay, right.
There's no replacing panels when it lands. They want it to be able to land. They want to be able to fill it up and it go again.
Right. Perfect.
That's their logic. I'm just.
Right, sounds easy.
Dead easy. And the worst thing is they want to be able to do it on Mars, where they can land at the North Pole and find water and CO2 and generate fuel to get back.
Yeah.
God, imagine the pressure when you land there and...
We're not close enough to the water. We didn't bring pipes long enough. We're going to have to do it in canteens.
God. Imagine just being that guy with 2 extension cords being like, here we go. 5 centimeters. Oh, poor bastard. That's one of those moments like Michael Collins. And if I say Michael Collins, you guys know who he is?
The guy who stayed in the
poor bastard who didn't go.
Yeah.
The poor bastard on Apollo 11 who didn't get to go to the moon. The one person people tend not to remember. It's just kind of like, fuck,
The guy who took the picture of everybody else throughout history and the future, and everybody on the planet was in it except him.
Yeah.
The worst case of FOMO ever. Worst FOMO ever. Every couple hours. Hey,
all right, we'll try that with chat. Can the chat hear me better now? Because apparently I was really quiet. So,
I can hear you.
Yeah, you guys can, but for some reason OBS is picking up my volume softly. So I don't know. It's being ridiculous. They'll tell me. I added a bit of gain. I added a bit of gain to OBS for me just to see if it works. They can tell me if it doesn't.
Oh.
Yay, better.
For the record, this is physics rope. It's perfect. It doesn't break.
You need to use a whiteboard,
Everybody
Chad,
knows
because then you
physics
might might win Sideman Dan's award for at Christmas. So.
Could you please make an elevator out of that?
An elevator out of that?
Yeah.
Oh.
I mean, I could
Wow.
put a person inside the.
No, space elevator.
Is that the?
I can flip it upside down. I mean, there.
Can we talk about the space elevator for a minute?
And you can again, it's that perfect fiber again.
We
It works
can,
perfectly.
but can we go back? There's a couple of questions in here. Sammy Jenkins
let's go back to
asked
the
us,
questions.
why is the absence of light black and not another color? And
Light doesn't have a color.
Yeah,
No.
and that comes down to our perception of color. I mean, what you and I might call black, Nerdy, could be actually perceived entirely different to the two of us, because our eyes pick
Not
up
true.
the electromagnetic waves. They don't actually see colors.
I
Color are
No,
a
I argue
against that.
representation of what the world is created in our brains. So our perceptions of colors are an artificial construct in our head.
Disagree.
That is true. Well, that latter part is true.
Yeah.
In
the eyes,
disagree with the first half. I agree with the second.
There's going to be variation within a certain range. I think that's just logical, but we can test out what wavelength certain colors are, and we can test out the receptivity of the human eye neurons and cones and what they're most sensitive to, and I think you can say that I see red, you see red, pretty much the same thing.
No, we can both say that we see red. We can't say that what I see as red is exactly the same as what you see as red. So the way my brain depicts red could be entirely different to how your brain does it.
That's what I'm saying about the little bit of variance that maybe your red is a little more pinkish than mine, but that it's still within this range of the frequency of
we
light.
actually have we are definitely
wavelength.
seeing the same frequency. No, you're right there, Jim. We will be seeing the same frequency. How we perceive that color in our heads, how our brain displays that displays not the right word, but how it
Perceives.
how it perceives that color could be incredibly different for each of us, because it depends on how.
No, I don't buy that. I just don't buy that.
No.
Well, we have
Because
no
at this
way of
point-
knowing. We have no way of knowing.
Yes, we do, and I'll give it to you.
Oh, okay.
So at this point, you can completely. Okay, so there's two things. First, when you're talking about color, yes, it's a social construct. It's a learned behavior, because you can only have to go to different languages that necessarily don't have words for different colors.
Yes.
So the fact that we point at something and with that wiggles a frequency and say red is a social construct. So then you want to talk about the perceived our perception. So at that point, we have the same eyes, we have the same optic nerves, and we have no reason to believe we have anything other than the same hardware. So I would argue we don't have any reason to assert that our perception is different. It's kind of like atheism, where we have to go with the null hypothesis.
Oh no! I think you're probably right, but we can't prove that.
No, but what I'm saying is we don't have to prove it, because it's the null hypothesis based on the fact that we have the same stuff. If I pick this pen up and drop it, if I do it again, it'll do the same. Same with our brains.
No,
I
I
have
agree
to go
with you.
with the default.
But it comes down to this is almost a presupposition, in a sense, in the same way that we have to presume that the universe we live in is real and actual, and we're not brains in a vat. Because
everybody, when you throw a rock at somebody, everybody ducks. That's a non-problem.
Yes,
Chad,
so I agree,
variable?
but we make, there are levels of assumptions we have to make that our universe is consistent at a certain level. Because there are certain things that we cannot know, and this happens to be one of those things that we cannot know, but we've got good reasons to assume that they are the same.
Apart from color blindness exists.
Yeah, it wouldn't. Yeah, but that doesn't matter.
But that's a difference in the eyes. We can actually see the difference in the cone. So.
Yeah, and that's not the point anyway. The point I was making is what I see as red could be entirely different to what you see as red. What the image is.
And this is where I was going to say you were wrong, because when we look at complementary colors, So red and green, and people perceiving them as opposite and very distinct. The contrast between red and green and the contrast between blue and yellow is something that we all identify and acknowledge are things that go well together. Red and green go well together.
But
Blue
that
and
can just
yellow
be a
go
social
well together.
construct too, because it's what we're used to.
Is it though? So you're saying that my aesthetic appreciation of the universe is a social construct? Now we're getting into some shit.
Well, we are.
So at this
I think
point,
it's a
you're
hard
saying that
one to
beauty
try
is a
and-
social construct. But at that point, I can't have an aesthetic experience. Yeah. So based on your worldview, we can't have aesthetic experiences devoid of culture.
I would also
And I don't
argue
think that's true.
that,
I think
don't think that's true.
like Chad, you're talking with color based on a pigment. If I talk about color based on light, which I'm familiar with from my background in photography, if I take two complementary colors and I put them together, I end up with white.
Well, yes,
Now,
but
we
when we
all
look at
see
the two
that-
colors
we all
next
see
to
that-
each other.
But we
We
all
look at
see
the two
that
colors
same-
next to each other, we see the contrast, is what I mean.
Okay, but what I'm talking about when you blend them, though.
Yeah, of course.
In a projector
I
light, you
agree
get
with
white,
you that we all see
and,
the same
and we all
frequencies.
see that same white.
We do.
I agree with you. We all see the same frequencies. It's our brain's internal perception of what the representation that the brain gives us of those frequencies that could be different between us, and we would not know.
And I thought that argument was settled last year when or the year before, whenever it was, when that whole dress became famous on the internet, the red and blue dress. And people
just
did
white
see
balance.
the same dress as
It's
to...
just white balance, people. Just fix your cameras.
But the point is, our brain.
I used to put that up in the classroom with the kids, and there were kids, about a third of the kids in the classroom swore blind that they were seeing different colours to the rest. And we were looking at the same photograph.
Yeah.
But that proves, though, that it's cultural. It proved because that's 100%. They know what caused that. No, they know what caused that now.
Yeah, I know they know
Wasn't
what caused it. But whether or not it's cultural is...
No, it's cultural in the sense that we know what time of day we get cues as to the colours from other things. And it was an interpretation of the light, and whether or not you are seeing, your brain thinks it's seeing it in the morning or the evening.
Yeah, exactly, because it has to do with the white balance of the picture.
Yes,
changing the
I
color
totally
temperature.
agree with the white balance, but why is the issue?
But that's exactly
and the why is
reason,
cultural.
Yeah. But
So we do perceive differently depending on...
I like the different way we
based
all
on our pupil size.
But I like the way we all look at this differently. I mean, I tend to agree with you, Chad, that it is probably the case that we all see exactly... Our brains all interpret the colour the same way, because we all live... Our brain is an evolved instrument, and it is probably likely that aspect of it has wired the same way in all of us. So it's very likely the interpretation that we all get is the same. We still cannot know that is the truth.
We don't see wavelengths. Our eyesight is effectively digital.
Yeah. Well,
but the rods and cones, like the iodopsin and the rhodopsin, are broken down by specific
it is
wavelengths.
quantized though.
Yeah, but my point is you're
fundamental
only
level
seeing a
quantized.
wavelength, or you're seeing 3 wavelengths. That's it.
Yeah. At the end of the day, the receptor pigments in your eye can only have so many states. So based on wavelength and intensity, essentially it's more or less binary, or more or less digital, like David said. Where, but when you're looking at the grayscale of things, again, it's binary, but it's binary encoded like brightnesses on a monitor, where it's goes from 0 to 255, right? Yeah. So when we're talking about digital, we're talking about not just 3 things, and then our brain does the work. Our eyes are still doing a lot of the work there.
So I don't like the analogy to digital, because
I think it's very apt, because a monitor works exactly the same way.
You lose information between steps versus analog. There's too much space in the...
And we do lose information. We don't see infrared.
Versus the line.
Oh, we lose information all the time because of our stupid nerves at the front of our eyes.
Yeah, but we lose information. In terms of losing information, I only have to point out that we've all done that thing where we find the blind spot in our eyes. Yeah. Have you ever done that?
Yeah.
There's information you're losing all the time, and you don't notice it. Digital or not, you have no concept of that blind spot. So you can't say, no, I see it all, when I can tell you, no, you don't see it, and then find that blind spot as a way to prove it.
They reckon, okay, I'm talking very outside my area, that you've only got...
We all are.
I know. Right,
That's
but you're
the fun.
only in focus, very visible. Right, if you take my window behind me here as being your entire field of vision, you're only seeing about that much of it clearly.
Yeah.
At any one time, your eyes are doing this and filling in information. You're only seeing a small area at any one point.
Yeah, that's the fovea, isn't it? That's like the fovea is where your cones are
just
most concentrated, and everything else is just much worse.
Scan line. Yeah, our vision updates in the same way an old CCTV display does with the
Which of course leads us to the whole thing that we all actually live in the past, because the amount of time for our eyes to actually process the image and our brain to process it and then feed us all that information and the sound that happens all at the same time, we're actually all living slightly in the past. We are not living in the moment. The moment has been and gone, and with them, our brain experiences it.
Okay, so now that's the cultural crap. What is a moment? If a moment is a nanosecond, or is a moment a moment? As we commonly think a moment.
There is a time limit for it, but I can't remember what it is. But
I was going to say it was defined at some point.
Yeah, it has been defined.
I can't imagine that its definition is beyond a half a second.
That's
when we look at the human eye, it seems that the human eye can only perceive changes in what it's looking at a rate of somewhere around a 30th of a second.
Oh, do you want to get the best thing? The best thing is the last few years, with the psychology of this, is brilliant. We think an awful lot of mental disorders involving voices, hallucinations, are really timing mismatches, because your hearing gets information way before anything else. Your hearing is like that, but for you to match it with your eyes,
the brain has to delay it.
Has to delay it by a huge amount in terms of its processing. And very often it means that you can hear voices.
And we all know how hard it is to resync sound when it goes out of sync, because it's a pain in the ass.
But you think you're hearing things because they're not happening.
Yeah.
And then it goes wrong the other way, and you're seeing things because then they cut. It's like a commentary afterwards.
But that doesn't account for say someone who's schizophrenic, who is actively hallucinating and hearing sounds and seeing things that are physically not there.
Because the voice in your own head is the same. It has to link in with the same timing. So if the voice in your head gets out of sync and comes ahead of when you're expecting it, you think it's someone else talking.
That I can actually see that as being kind of making sense. I haven't seen any data behind it.
Schizophrenia one, I have seen data behind.
I trust you on that one. I'm just saying that's my degree of skepticism of the word. But it
I
sounds
won't believe
like
until I can put my fingers in the holes.
Yeah, pretty much. You laugh. I've had a lot of terrible lab experiences.
What are you putting in holes?
What's that? I nearly killed myself with a high voltage power supply once, and I also lost part of my tongue. Okay, I'll tell you a stupid story. You know that one scene from a Christmas movie where they're like urging him to stick his tongue on the flagpole?
Oh, God, yeah.
Stuck there. He's like, ugh. So I was having me being the physics guy that I am, this is back during my undergrad, so many moons ago. I was thinking to myself, well, in principle, if you have a large heat sink like a flag, like a flagpole, putting your tongue on it, yes, it's because it's a good thermal conductor, it's going to cool the liquid on your tongue quickly, therefore causing it to freeze. But I've never actually experienced this before, so I'm like, well, would a tongue actually be able to melt itself off of a flagpole was my question, if given enough time. So, being the good empiricist I was, I decided to run an experiment. So I grabbed a copper pipe and a dewar, and then I went downstairs in the chem department and got my liquid nitrogen. So I got back upstairs,
this is already
put the copper tube in the dewar, let it get down to temperature. I don't know why I let it get that cold. And then I put on a glove, at which point I grabbed it. I was smart enough to wear a glove. But I'm sitting there like, Now, it burned so much, I immediately pulled it away, and it took off about a third of my tongue initially. It grew back, but I lost a couple of, taste buds on that one. It was a bad day.
That is bad.
God, it's so nice to hear you say that because you're so smart, and it's nice to know that you're so dumb too.
Are we all that though?
It's a wonder I'm alive. It's a wonder I'm alive.
You talk about that power supply thing. When I used to do repair works on phone systems, and because you're only dealing with 12 volts, if you had and it's low amperage as well. So if you had a circuit that wasn't quite working properly, you could bridge it with your fingers and see if it came up, but then you'd know that you needed to replace that part. You just get a bit of a tingle when you did it because it was fine. You knew it was safe. The voltages weren't high enough to kill you.
Yeah. So in this particular lab, why I had access to all this stuff is I was actually working at the university over the summer designing some new labs for the incoming students. And so I basically had free access of the senior physics lab, and they're just like design experiments for students, and I'm like, yes. So I basically just got to play around all the time. Yeah. But what was I got a very short-term memory here. We were talking about the
power supply.
So the power supply that I was working on happened to be 0 to 1.5 kilovolts. And the problem with the power supply was, and my whole point about taking this thing apart was I was servicing the electronics.
Yeah.
The whole problem with it, as it turns out, was a grounding issue insofar as the high voltage capacitor that should have been grounded wasn't. So when my screwdriver went in, I got kicked in the chest. And if you've never been hit by a high voltage current, it's everything in your chest goes immediately, and you just immediately seize and kick back. It was unplugged, obviously, and it was a one-time shock, but it's definitely something that's going to wake you up. And accidents happen. I mean, you have to be careful and take precautions. I took precautions, but that was what was broken about this.
So my experience with a high voltage power supply was with a 5-volt system that had a high voltage power supply attached to it for something else. And because of my experience with phone systems, I knew this part of it was 5 volts, so I thought, and I knew there was a fault in it, so I thought, well, I can bridge the segments until I find the bit that's wrong. And what I didn't realize was the high voltage unit was shorted to the 5-volt system. So when I touched it, it threw me across the fucking room.
Oh yeah, it's an experience you don't forget.
Oh no, you don't. It really hurts.
I'm a bit of a handyman, so I do some carpentry and electrical work.
Yeah.
I don't even, at this point, bother unplugging the walls just because the way I do it, I get hit just little twazes if I make a mistake. And it's nothing compared to what I've lived through before, so it doesn't bother me at this point anymore to get a little zap. So when you're talking about putting your fingers in the holes, that's Tuesday.
That's bloody dreadful. Yeah, but the stupid part is you know when you do...
120 AC is one hell of a lot stiffer than 80,000.
It's not the volts that kills you,
low,
it's the
low amp DC.
Yeah, but it's knowing the tools that I have and the contact times. It's not a problem. Anyways, I'm safe enough that I just get a little woohoo.
Okay.
You're probably with high voltage control systems because this was in a printer actually, which had a 5-volt control system and then a high voltage high voltage line. So the high voltage line that was used for charging corona wires was actually shorting to 5 volts. Yeah, so you don't. Yeah, you don't want that because there's an awful lot of current going through there. Like I said, threw me across the room.
That would have had to destroy the entire motherboard or wherever the 5 volts.
Oh yeah, it was fucked afterwards. Yeah.
Okay. This one's really good. You'll appreciate this. You guys know what a Jacob's ladder is?
Mm-hmm.
Yeah.
With basically the two little prongs. Yeah. It's in the background of every 50s sci-fi movie.
Yeah. That and plasma balls. Where you put the fingers on the outside and they.
Yeah. So going back to our earlier conversations about microwaves, I took the transformer out of one of those, and I basically decided
they all start bad.
And I still have it. I actually made a little Jacob's ladder out of some old, basically one of those transformers and some coat hangers. But when I was using it, and this is again back in my early teaching days, I was actually giving a presentation about how to incorporate these things in the classroom. It was actually during like a PD day thing. And I accidentally, in front of a room of about 30 other teachers, gave myself a shock off the Jacob's ladder. And it was...
How did you adjust the air gap?
And I was like, yeah, that's exciting. Okay.
Chad, how did you adjust the air gap in that?
What's that?
How did you adjust the air gap at the bottom?
So I have 2 wires that are just connected to some coat hangers. And I have screws that go into a piece of wood.
Yeah.
And essentially I kept them a certain distance apart, and then I used another piece of wood to kind of push the bases together until I got the spark to go.
Okay.
So basically...
I have to ask Chad, have you built a Tesla coil?
No, I don't have that kind of kit.
We'll see.
That'd be fun.
Yeah.
I haven't done it either, but I want to.
Let's do a do-it-yourself show.
Build a Tesla coil. Yeah.
How many of us can we kill?
Yeah.
How many of us can we kill?
I'm invincible.
We were filming building the Tesla coil, and then we turned it on and we destroyed the camera.
Yeah.
Or we can get somebody else to do a complimentary.
You'd have to build the Faraday cage first.
To build your Faraday suit.
Oh, I would love that so much. I've always played around with the idea of taking chicken wire and putting around a classroom to cut out Wi-Fi signals, to cut out cell phone signals for students, just to piss them off for a day.
That would be so cool.
Just ground the whole wall of the room, and they're like,
But you'd have to have it at the right. You'd have to have the right gap in it to actually for it to block the right.
I'll be right back.
If it's fully grounded, you're fine. It's enough. Yeah. Anyway, I've always wanted to.
Have you seen the latest 5G cases? The anti-5G cases to put your Wi-Fi router in?
I have not, but dear God. I don't.
Your Wi-Fi still works.
These people are stupid. Okay, Catz. We've heard Chad's stupid things, and I've said mine. You must have some. You have to have some.
I was going to say.
Nothing with electricity. I've done the same thing 4 times. Now, if stupidity is not learning from your mistakes, then the most stupid thing I've done is set my sleeve on fire 4 times doing the same thing. And I don't know if Chad's rooms at school are set up like this, but the gas taps on the teacher's desk are those gas taps that come up, and we have 2 taps per pipe.
Yeah.
And the amount of times I've been teaching and wanting to light a Bunsen burner, when I've connected the Bunsen burner to one of the taps, and I've turned on the one that the Bunsen burner isn't connected to because I'm speaking, and then in front of the kids, I've had my match and struck it right next to that tap, and obviously I've just set my sleeve on fire, and I've done it 4 times, like not just once, I've done it 4 times.
You've survived 4 times.
I did survive. Once I lost half an eyebrow, like it was really bad. I took almost all the hair off my arms. It was bad. Only once did it really hurt. Like the other 3 times I was, but once actually was quite nasty. I had to wrap
Did
up.
you maintain your composure in front of the class?
Of course not.
No. Being me, I only had 2 options. One, I knew the kids were going to laugh and take the piss. Language. One, I knew the kids were gonna laugh. So I either had to be laughed out or laugh with good. So we all broke down. We had a good laugh. I pretended it didn't hurt, and we cracked on.
I've knocked a soldering iron off the table before that was on, and I knew it was on and caught it. That hurt.
Oh,
yeah,
wow.
that really fucking hurt.
I've had it fucking land on my leg.
Oh, yes.
Go straight through my pants. Like gouge my leg. Oh, forgot about that.
I've done that at home. I was cooking and I had a skillet in the oven doing some cooking, and when it was done I just reached in to grab it. I went to hot pan. Burned the fuck out of my hand for like, well, you know.
It really hurts when you do stuff like that. You go, I'm going to drop it, I better catch it. Oh shit.
One of my little Chadisms that I always repeat to people is like, that's the name the students started giving my weird little sayings. So one of my Chadisms is my disclaimer got so long I forgot what I was going to say. Damn it! Words, come back to me. Nope, it's gone. It's gone. Never mind. What were we talking about?
Ooh, Nerdy's got a good question.
What was that?
Which one?
Nerdy's got a good question.
What was
Which one?
If you want to knock out all the electronics on Earth, how strong would the EMP need to be?
Oh God.
I'm not familiar with EMP tech, so at this
and would it
point
have to be?
where-
Would you need multiple EMPs?
Yeah,
does it
because
globe shadow?
the Earth would act as a barrier to the EMP. So
You want something that's going to induce a current in the
unless
grid.
the Earth's flat,
Yeah.
in which case you could be at one end of the Earth.
at the North Pole.
No, but because the Earth's spherical, you wouldn't be able to do the whole Earth with one thing. So you'd have to have multiple satellites around the Earth, or
See,
actually,
I'm
way
thinking-
more efficiently, if you launch multiple nukes into space and you detonate them at the right height, and that will create an EM pulse that could block out the. Of course,
I'm not convinced that that's true, because if you think back to radio signals back in the 50s, in principle, based on radio waves bouncing off the ionosphere, you could pick up Radio Moscow in the Americas. So there is a degree of reflection of that kind of signal. I don't know what the magnitude of it is.
It gets trapped in the different layers. When they did one of the first nuclear tests in the Pacific, they screwed up radio waves for days, radio signals.
Yeah.
But only
So
for
creates
certain
the impulse.
frequencies.
So you're saying it gets trapped in that layer?
Mm.
Okay, so if that's the case, then getting trapped in that layer means that a local disturbance is going to distribute naturally.
But that's not going to damage the electronics. It's not going down to the next level. That's not going to damage electronics on Earth.
Yeah.
But that's just a question of magnitude. Now, if the signals get louder and more gets trapped, anything that's trapped has to radiate away. So it either goes up or it goes down. The stuff that goes down is what the people on Earth have to worry about. So in principle, you just have to have essentially twice the amount of necessary energy trapped in that ionosphere so that you have half of it coming down.
That would
In
still
principle, it's
probably
possible.
take multiple.
I don't know
nukes.
if
Would and I'm would there be
Well,
some kind of effect
I don't know.
where
I don't know.
would there be some kind of effect where any kind of if you had like ridiculously big, I'm talking about just unbelievably stupidly big, like electromagnetic pulses hitting the ionosphere, that would obviously induce a movement in the ions in the ionosphere, and even if that was trapped in the ionosphere, as those ions move, they would generate their own magnetic field around it. Which would that have to be trapped in the ionosphere, or would that hit us like a secondary induced field?
Well, in principle,
The problem is, I
electric-
assume the magnetic field where it would collapse that's holding it all together. If you went to the sort of strength required.
But here's the thing: as an EMP, it doesn't have to be a long-term signal. We're just looking at a delta function here. It's,
Yeah.
I mean, it only has to be big for a second, like it doesn't, or a moment even.
It only
It
has
just-
to it only has to induce that electrical current in the.
But it
the
needs
thing,
to move
what?
across it
Yeah.
for long. It needs to happen for long enough. I think if you hit it with that much energy in one go, it'll just blast straight through it. I don't think it's going to distribute across it like it would with the nukes.
But that's why you hit it in
no,
multiple
no.
spots all around
No.
the world.
I would think that would depend on the run of conductor you have. When electricity finds the right path, it's there yesterday. You cannot respond to
it is
electricity
instantaneous.
in any kind of adequate time to prevent its damage.
Just for the sake of the chat, I will say this: when you have electricity in a wire, it does move instantaneously. The energy is actually traveling in the field contained in the wire, not the electrons. The actual electrons move nothing, basically.
40
enough
miles
to
an
make
hour,
things move.
30 to 40 miles an hour.
And a
yeah.
nanosecond is only about 9 inches long.
Yeah, I mean,
Travel
these
time for a
things-
nanosecond.
So this happens fast, and that's what we need to be considering here. Is again this is why I'm wondering in terms of EMPs. If we're talking about nuclear explosions, those might not be the way to generate EMPs in this destructive nature. Given that it
I
has
was
to
thinking
almost
about
be
an
an array.
X-ray, nuclear-powered X-ray source. The ones designed for stuff.
That's actually worse because a nuclear powered X-ray source would also be damaging to organic matter too.
What we're ignoring though is that the danger is not from EMP, human-induced EMP. The danger is from a gamma burst radiation from the sun, like they had in the middle of the 19th century, that wiped out their newly formed telegraphs and things like that.
Carrington event.
No, well, no, it's still it's not gamma. It's high energy particles in the ionosphere.
Well, that's what I was
see,
saying. And you need enough to induce a current across the electrical grid as it currently stands, so that basically the grid then acts as a distributed EMP.
Yeah,
But we've seen that the sun has that capability.
You don't actually generate that in the smaller amounts of smaller electronics themselves.
See,
I mean,
you guys are assuming that it's coming from the sun. If the Earth gets into an argument with the sun, we're not going to win. So I'm not worried about arguing with the sun. I'm more worried about, let's say, Russian, Chinese, American weapon. These are the kind of EMP devices that we really need to worry about, because those will be on the order.
One of them now. The grid is too interconnected in the States. You've seen what happens when relatively small.
Yeah, but that has more to do with the loading of the grid, not necessarily, and the maintenance of it, as opposed to an EMP surge per se. Like that EMP surge came from regulatory issues.
Yeah.
So I mean, yes, it's bad, but it's not.
It does take a long time to repair,
it's not
though.
Terrorist bad.
My point, though, is that could be generated relatively easily, locally with a generator generating the EMP.
But how do we do? And that's the thing. But does that technology exist outside of a nuclear device? I don't know.
Yes. Oh, you can generate EMPs.
Yeah,
relatively.
you can generate EMPs. Yeah.
On the scale, where we can blast things at distance.
Oh, the issue you've got is getting it there. But yeah,
and that's the thing. Like,
why not?
Because where magnetic fields go, electric fields go off as 1 over r squared, but magnetic fields go off as 1 over r to the 4. So I mean, if you're talking about EMP influence, it has to be local.
They're also directional. That's one of the other problems with EM generators. They're directional, so you'd have to get it somewhere near a grid station.
Yeah.
And apply it into it. And if you're that close, you may as well just blow the grid station up.
And that's where we are, right? So.
Yeah. But one interesting thing about EM pulse generators is you could technically build one into your car and direct it away from your own engine, and then if the person in front of you is annoying you, deliver an EM pulse to the car in front and kill their computer.
Yeah. Okay. Now, but on that point, when you're talking about having EMP level things in cars, you already have those. They're called speakers. I mean, they don't knock out people's engines. You don't point your speaker at somebody and have the electric field.
The police were testing a device, and I have no clue whether or not this has entered production. But it will that you can shut down a car.
Yeah, I've heard and tried to investigate that too, and found no truth to it.
No truth to it.
Sounds like witchcraft.
I was intrigued. I had what I read was a report from a police test thing, but I don't know whether or not it went, because I think they found it ill-effective on older cars.
Yeah.
So basically, you look at the roads on America having the device.
You can't
because the only thing you can damage is a computer system in the car with the EM pulse. An older car which has a distributor and everything is just going to go, a little blip, and keep driving.
Yeah, keep going. It'll make a difference to it.
Yeah.
Well, the coil might get a little excited. I mean, that's you give a coil too much power in, and it's going to blow its little brains out.
Anyway, guys, we've been going for 2 hours, and Catz and I have been going for 2 hours now. I'm thinking it's probably time we start winding up.
I have an interesting question about whether or not a speaker made of superconductors with a supercapacitor would create a weaponizable EMP device. But that's a conversation for another day.
That sounds like a great conversation. I want that conversation. Hold that thought in your head.
And something you probably shouldn't have, where the NSA has access to the conversation.
Yeah. This stream is taken down for security.
I'm a very dangerous man.
I want to thank you all for joining me. It's been absolutely brilliant. I haven't got everyone's link in the description. I have Catz link down there, so please, I'm pretty sure everybody in the channel is following Catz, but if you're not, please go and follow him and sub to him. He is absolutely brilliant. Most of you know Dave, and go follow Critical Cripples and sub to him for
all your critical cripples.
I can't. My mouth doesn't want to work. Will's not going to be happy about that. And thank you, Chad and Jenny, for joining me. It's always a pleasure to have you guys here, and I think I learned way more than I can ever teach anyone. It's been awesome.
Thanks for having me. Always a pleasure.
Thank you. Did you have anything you particularly wanted to shell out, Catz? What have you got coming up?
Very little. It's been a long time since I've released anything. I need to start maybe making videos again.
Or at least do a couple of streams. I mean, you could always invite some of us on. We'd love to do a stream.
He's lying. He's on agree to disagree every other day.
Yeah.
Well, once a week we do. Yeah, agree to disagree. I keep forgetting about that. Yeah, once a week. So we have got a debate. I'm debating Brandon Toy off Ranty's old channel next Wednesday on that. Next Wednesday afternoon.
Awesome.
So
I liked your no evidence guy of a couple of weeks ago. What guy with 3 names?
George Howard Stewart.
Yeah, that's him. What a
Let's let Jen finish up the stream, and we can keep talking after.
All right. Thank you, everyone, again. Please check everybody out. You've all been amazing, and next week, because of Christmas, there'll be Purple's Christmas marathon, which we're all most people on here are taking part in at some point or another. I think Jenny's trying to do the whole lot, which is 40 hours, Jen?
No, it's so far I only counted as 24. Perp mentioned it was going to be 40, but it doesn't look like it's going to end up that way.
It normally extends just right up to the wire. It gets a bit patchy up, and then on the last day or so, people fill in, and it ends up, and then we have to do this massive.
So I'll be providing 24 hours of stupid.
You'll be fine.
Highly qualified.
Ooh. Wow.
So that would be awesome. Something for anyone to check out or get involved in on Christmas. And I believe it starts Christmas Eve and we'll go a little bit into Boxing Day. So anybody who's alone over Christmas or just has a bit of spare time and wants to catch up, tune in. There is a list that will be published that will show when all the different people are taking on over. There's a playlist. That's the word. For that, and people will be able to follow that. It's going to be a lot of fun, so please go and check out that and follow Purple if you're a bit unsure of what's happening. So yeah, thank you again, everybody, and I will catch you then. Bye.
Something selfie stick.
Something.